We have here Cesare, who's CEO of Hex5 Security. He's working heavily with the trust execution environments, and he'll be talking about multi-domain RISC-V trust execution. Please welcome him and see us talk.
Yep, can you hear me? Yes. So first of all, we'd like to ask you to come here. I want to show you the people who actually been involved in the project, give them some credit. Some of them didn't sleep much in the last few nights, so a little bit of thank you to all of them. You want to just say your name and just...
Yeah, sure. So, Boran, nice to meet you all. Daniele, Sandra.
Very good. Thank you. So what is security? It's many things, different layers, obviously, right? So one of the other presenters showed that well. So this is kind of security that goes as close to the hardware as possible. And in security, there are a few key concepts. This is the concept of security through separation. What does it mean? It means that you can always attack a system through the weakest point, which is called the entry point for the attack vector. But there's something typical in any kind of attack, which is the lateral movement. When you move from where you got in to what you really want to get. And so even in the physical world, security through separation is a mean to create these barriers. You can call them containers, you can call them domains, zones, but they are intended to solve this very problem, which is, if you get any system these days, that's what we learn in school, right? What we learn in school is that you get different pieces of functionality, you write your software, perhaps the operating system as well, the libraries, whatever. You pass them through compilers, then you have a linker that resolves the references, but in the end you end up with a monolithic piece of software that shares resources. And I know what you're thinking of, well, but how about virtual memory and MMUs? I have a final slide for that, but in terms of security, that's not necessarily a good idea either, okay? So let's see how this evolved over time. So a few years ago, ARM, the incumbent, came up with something quite good to make my friend Tim happy, okay? But no, it's honestly it is, because it really makes a difference, because it addresses the problem. It addresses the problem. And the way TrustZone, which is recognized in the industry as the way to secure things, does it, is by cutting into this, right? So vertical cut. There is one bit, to make it very simple, that goes up or down, and you either are in the secure world or in the non-secure world. And that's a good approach to that. And now we get to RISC-V. And RISC-V doesn't have TrustZone. What does it mean? That it's not secure? Is that where we are? So this ends my presentation. Any questions, right? Hopefully not. We can do something better, okay? And so what we can do is to extend the very same concept of TrustZone, but this time make it multi-zone, which means that instead of having secure and non-secure, what we propose as an open source standard is to have a multitude of these. How many? I get this question all the time. We have these bi-weekly calls, and you say, what's the number that you... It depends what's your application. But for sure, it's more than 2. Otherwise, you have to put... If you have 2 secure things, where you put them together, then each one has to trust the other one. Now, the way you make this work is by adding some thin layer of software on top of the hooks that are built into the RISC-V core itself. That's the other question I'm asked all the time. So is this software solution or is it a hardware solution? It's both. But what is innovative is that the hardware part is already baked into the RISC-V core. What this thin layer of software that definitely fits the boot ROM, it enables it. And it adds a lot of other things. So let's see what these things are, okay? This is something that we use for the investors. Investors don't really understand all it is. What it is, it's like Docker for silicon. Okay, I get it. If you point your camera to this QR code, you get directly into the GitHub repository. All of this is on GitHub. It's freely downloadable, okay? So probably not a good idea to do this right now because you lose the presentation. So what you get with this kind of API, and I'll go into the details and show you what it is, but just to give you a sense, right? It's free and open as it is RISC-V. RISC-V is a free and open ISA. This is a free and open standard. It's maintained by my company, X5, but it's provided under the most permissive licensing that you will ever see, which is the ISC, which says do whatever you want, basically. Yeah, just don't hold us liable. It gives you an unlimited number of equally secured zones. That's another difference, right? So there's no concept of something being more secure than something else. Because again, if you break in into the weakest point in the chain, and then you're in. So everything needs to be, but what is also very interesting is that with this proposal, what you can do is to map all the resources that are in the system to specific domains, to specific zones. And that's not just your code, your text segment, or your data segment for the RAM. It's every peripheral, and you'll see an example. So if you have a UART, if you have GPIO, if you have interrupts, this is something very interesting too. People tend to miss this point, right? So you build all of this beautiful thing, and then one interrupt comes in. And guess what? The processor goes up to the M mode, which is the highest level of privilege, and your interrupt handler runs as God on earth and can do any kind of possible damage. That's not a good idea. That's not a secure system. So what you want to do is to have this kind of security context and have your interrupt handlers being mapped to each one of them and being executed in user mode, where they cannot create damage, not to the rest of the system. As I said before, it's key. It has to be enforced by the hardware. If it is pure software, it's not going to work. At the same time, if it is completely in hardware and you have two, and then you are limiting your flexibility. So you really want a mix of both. You want to be able to define your policies, but also you want this to be enforced by the hardware. And just to make clear, policies are read, write, and execute. It's not just saying, this domain, this application can use this bit of RAM. It also can use it only for read, write, rather than read and execute. Or if it is, for instance, we have an example, you'll see a real-time clock, just read it, that's fine. There's no harm in reading the real-time clock. Now, if you do things well, and I've been doing this for quite a number of years now, you realize that the moment you say, hooray, I was able to break things in pieces, you say, gosh, now what do I do to the system? It's not going to work. Because you cannot place a call on the stack. You cannot call an API. There's no stack. It's not shared. It's completely separated, okay? If you look at the model that I showed before. So how do I call an API? How do I receive something back? How do I make the system work in the way I was taught in school? Well, you don't do it. That's the whole point. You use a system of messages. And what's the major difference is that messages are designed by the system designer. It's not any possible thing that is in an API, whether it's disclosed or not. If you don't define a message, nothing is going to happen. If you get messages that you don't care about, you just ignore them. It's a way more robust way to develop systems. And by the way, in this case, there's no shared memory ever. Everything happens in the core itself without touching the memory. That's by design. But if you are in a multi-core situation, we support completely Linux, by the way. Okay? And so then you have inter-core communications. And whether it's Linux or anything else, that's not the point. When you have multiple cores, you have to have something that they share, but they share in a secure way, because it's still protected by the same policies. So you cannot go out of buffer because there are no buffers. You cannot do any kind of attack to the stack because there's no stack, and so forth. As I said, interrupts is a requirement. It needs to be mappable to your domains. But they also need to execute in new mode. So I want to spend one word here because this comes up in all of our calls in the security group. So do I need end mode? End mode is the user mode. That's a totally different story. That's a delegation mechanism where a higher level of privilege can delegate interrupt to a lower level. It doesn't map that execution to any context. The core doesn't have a concept of any context, okay? So end modes just speed up this, but they don't solve the key problem, which is how I define these security containers. Now, if you have code and you want to touch it, and you want to run it in a secure way, you have to have full trap and emulation. Because the moment that you put there a privilege instruction, the only thing you get is an exception. Everything stops there, not much fun, okay? So these are the kind of things that you have to build on, and we want to build them in a standard way, okay? So trap and emulation for privilege instructions, Soft timers. The core has one timer. What is Rich? Rich needs one timer for FreeRTOS. That's good. But what if I have 3, 4 zones? I have one timer. How do I maintain the system working? So you also need to build soft timers or some way to recreate the timing. This is about interrupts, right, in the system. And also you want to have this boot in a secure way, because if you do all of these beautiful things and you go there and you just hack the image and you completely clear these policies, is not good, right? So what you get, and I'm going to go into all the details now, but I wanted to give a sense where we are going, right? So no need for proprietary hardware. All you see here, all of this proposal is based on specs 1.11. It was 1.10, now it's 1.11 ratified. 10 to 11 doesn't really make any difference as far as what this covers, okay? And basically any core, any RISC-V core that has the U mode and the relative, PMP is physical memory protection, okay? It's already there. So this is also the beauty of this model. You can retrofit existing applications. You don't need to upgrade your hardware to get in a secure situation. The hardware is already there, you just need to use it, enable it. No need to change existing user code. That's another major innovation. And I can show you the demos. We have demos actually running there on the desktops, tabletops. You can have literally precompiled, fully linked binaries. You drop them in the zones, they just work. That's good, right? Because every time you touch your code, you risk to create damages. This is not the kind of situation where you rewrite your stack or anything like that. In one zone, we run FreeRTOS, and FreeRTOS runs really well, okay? Final one. For the thin layer of software itself, this is also very innovative. There's no need to compile, link, figure out what kind of version of the compiler I need, but then I compile the rest with some different options. Do I have what? No, you don't even see it. You will see in a second, it's a new concept, it's a new approach. It's an extension to the toolchain. So the security comes up as part of the toolchain. So you don't need to compile, link, or defines, or whatever. Okay? So let's see what we do with this. This is a real thing. So we presented this some time ago, but it's also working there if you want to see. There's a little robotic arm that moves. Okay, so you need some hardware. And in this case, we use FPGA because that's obviously what's more abundant these days before we get a lot of silicon in production. And what we did was to put on this a modified version of what it is in the end, the rocket, right? And so to give credit to the maintainer of GSI-5, they are the maintainers of the E300, which is an overall SoC around the rocket. And we did some modification as well, mostly to use the Ethernet here. But any core, as I said, would work as long as it has PMP and it has the U mode. This is what the hardware does, provides PMP. Now, on top of that, in M mode, and so for people who are not super familiar, M mode is the machine mode. As the model is always there in any RISC-V core, otherwise it's not a RISC-V core, and it's the highest level of privilege, okay? So there you put this very thin layer of software, which is, again, open, free and open APIs, and you get the messaging there. And so what do I do now? I start building my system. And so my system has FreeRTOS. And what FreeRTOS does, well, moves the robotic arm in a nice way and turns on and off some LEDs connected to the GPIO. It's a simplification of what is your actual application, right? And so we all love FreeRTOS. It's there, does its work, nothing really special to say here. Just point out that to do this, to move the robotic arm, which is connected over this SPI USB, I need access to GPIOs and some interrupts. So what I do, I map to this zone just the physical resources that I need here. I don't map the Ethernet. This guy needs to move the robotic arm, not to be exposed to attack on the Ethernet link, okay? Well, it's an IoT device. I stands for internet, so I need some connectivity. And so here is the first time that you see how this works, right? FreeRTOS comes with a full-blown TCP/IP stack. Good, but then it becomes monolithic. And we learned in the past months that some vulnerabilities were there that would expose the whole stack. Not a good idea. And so what you want to do, and this is the key concept, right? So instead of being a vertical stack, you turn it 90 degrees, and so you have independent models, containers. They can fail individually, absolutely. The damage will not spill to the other ones. Faster? Is that what you're saying? Okay.
We're out of time, actually.
We already have 25, no. I started later. No, it's 15 minutes.
Oh, sorry.
I have 10 more minutes. Give me
I thought it was 15 minutes. Actually.
Just because of this, I'm going to get 2 minutes more.
Go ahead. You get 1 minute more. Thanks.
I go faster anyway. Okay. So now in any system that has any kind of crypto, you need to have a root of trust. Now, the good thing with this model is that the root of trust is separated from the rest. Same story. You cannot get the keys out by attacking like crazy the TLS link. And by the way, we have done this with Wolf SSL, another standard, de facto standard for embedded. We just drop it in a zone. It works. That's the beauty of the model. We didn't have to reinvent the wheel, right? Again, notice that this layer, which is the user mode interrupts, the Ethernet is only for the TCP/IP, so it's connected here. But anything that is related to the root of trust is specific to this zone. This is the hardware mapping. And then finally, we have just a console here that uses the UART. Nothing special there, it's just this local. So you can see this as the safe and unprotected side. Okay, so here is what it looks like, the API. The API is composed by 2 components. One is the data model, and the other one is the library itself. So the data model, to do whatever I said, you, as the developers, are exposed only to this level of complexity. So if you can write this file, you can do the system. Let me repeat this. If you can write this file, you can get the system I just showed it to you to work. And it's on GitHub. Try it yourself if you don't believe me, right? So I'm just going to go in the details of the first one here. So you define a set of zones, as many as you want. In this case, we have 4. And for each zone, you do something like memory map the resources, and you say where they are and what they are. So zone 1 is using this bit of flash, and in fact can read and execute. This bit of RAM, and in fact can read and write. By the way, also uses the PWM, it changes the color to LED. And if you remember the schema there, moves the robotic arm, GPO, and PLC. This guy uses the Ethernet. And this guy uses nothing at all because it's the root of trust. Now, look at the interrupts. They are specifically mapped to each one of the zones, okay? And so, as I said before, you get your executables, binaries. We just announced, we showed there, we are working with ADA core. So you can have one of these zones that runs ADA software, the other ones can run C. It's absolutely fine. The system has no concept of what is running. They come together with that yellow part, which is the kernel and communications, and this policy file. And then at the end of the toolchain, you get something that in 300 milliseconds, basically, cranks out your signed image. So you also get secure boot as a byproduct. And this is the last slide, so I think I'm running time. So here's the whole API. And here's another key concept, right? You're talking about security. Attack surface plays a role. The simpler, the better, more resilient. You want less if you want to get more in security, okay? So let's go a little bit. So first of all, permissive licensing. It literally says do any purpose, whatever you want, commercial or not, that's fine. This is the API definition, okay? These are the 2 calls that you can do, if you want to do them, to do yielding. So that's to make the system very responsive. The system is preemptive, okay? That's just to guarantee the safety. Anything goes wrong in a zone, the system keeps going. It's hardware enforced. But if you want to make the system more responsive, you want to yield when you're just looping to the other zones, right? And so that's how you do it. And the WFI is not a 3-letter bad word. It's waiting for interrupt. That's for people who know it. It's to put the system on suspend and low power. And this is the send and receive. It's that simple, okay? And as you can see, to get the system going and send and receive messages, you cannot spoof the source of the message. So this is rock solid. You can ignore a message. You just say, I want to send a message to zone number 1, 2, 3, whatever. And you send a pointer to your local zone buffer or whatever you have as a data structure. It gets passed over the link. That's it. And this is how you register and interrupt those user and mode interrupts. So just one call. It can be easier than this, right? So here is this little bit of difference in between traps and interrupts. In a sense, one is synchronous, one is asynchronous. And so whatever is actually synchronous interrupts are mapped for each zone, but every zone gets a full set of traps. We don't have time to go to all of these details. And This is how you enable, disable interrupts. No much surprise. That's the way you would do anyway with assembly. Right? And this is a whole bench. This is a soft timer, and this is a whole bench of privilege mode instructions. If you try to run them in U, you will just get an exception. In this case, they just magically work because they strap an emulation. And so here is how you put together a piece of software. This is actual software. And so the system is here. So this is something that's already built into the new GCC. It's the user mode for interrupts. Nothing special. You're familiar with this. This is your interrupt handler. Whatever is the logic. Here you press a button, it turns on the light. But this is the idea, right? How you actually get this working, you have some initialization routine in your main or whatever, and you just register this interrupt. You say, the button 0 interrupt handler, which is an interrupt in user mode, is associated to to interrupt number 11. It's the pen for that. 11 is the external interrupt for people who are familiar with this. And here is how you send a message. And so this whole piece of thing, what it does is when you press a button, there is an interrupt handler, gets the zone into context, executes the interrupt in user mode, and sends a message, if you want to see the demo, then on the screen says, hey, button number 1 pressed, something like that. And with that, I would just point it out that all of this is free and open as a standard API, up to you to implement it, or you can look at a commercial implementation. We do dual licensing, so for commercial use, it's licensed, and for academia, research, evaluation, it's totally free, which is the common model of dual licensing in this kind of software. Any questions? Okay. No, really, thank you to all the people that actually contributed.
And now, indeed, we have time
over
for
months. Okay, so we do have a question, right?
Hi, could you tell me the scheduler? I want to know how to schedule. It's okay.
I cannot hear you. Sorry.
How to schedule each zone? How to CPU schedule?
How do you schedule each zone?
Yeah.
Okay, so if you remember that, let's see if you can go quickly there. That's a good question. Thank you. So in a very simple way, so all you have to do is to tell to the scheduler what's the tick time. The tick time is not, so don't get confused, it's not that the system gets stuck for 10 milliseconds for every zone. It's not like that. That's your safety valve, right? So if something gets stuck after whatever time you put there, it moves on to the next word. So that's all you say. Now, if you put 0 there, it's completely cooperative, which means that eventually one zone can stall it, and I would not recommend for safety-critical applications, but otherwise, that's how you do it. And so you get both the preemptive and non-preemptive just by setting this number. So simplicity, again, less is more in this case. And that's a good question. Thank you. Any other questions? Okay, so I think it's... Thank you.
Thank you, Cesare.